Okay, so welcome to our first concept lesson. Today's lesson is charge and Coulomb's law. And today we're not doing a lot of math. That's tomorrow's lesson where we just do example after example after example. All right. So the first thing is we have to understand that something I mentioned yesterday, that charge is an intrinsic property. It is an intrinsic property. And not all particles have it. Okay? For example, a neutron and a neutrino. They both have any U in them. Meaning they're neutral. They do not have charge. So not every particle has charge. Does that make sense? Okay. Other intrinsic properties are things that, like a particle has to have to exist. Mass is an intrinsic property. There are massless particles, believe it or not. For example, the photon, if you think of light as a particle, which is debatable, but if you do think of light as a particle, it is a massless particle, if that makes sense. So it doesn't actually have mass. So later when we study the momentum of light, it has nothing to do with mv, because there is no m. So we will talk about momentum of light at a later time, probably after the AP test, but momentum of light is not measured by mv. Interesting.
Is it...
Another intrinsic property that some particles have, not all, is what we call color charge. Color charge. Not very many particles have it. Like when you think electron, you think a tiny mass with charge. But you don't think color charge, because color charge is something entirely different. And electrons don't actually have that property. Okay, but they have a property called spin. Now you might think you know what that means, but it doesn't really mean spin. Okay, a lot of these words were chosen because they didn't know what else to choose. Okay, so I'll mention that again. There are other intrinsic properties. Okay, mass, color charge, spin, etc. Let's go and talk about electrical charge. There are two types, positive and negative. Okay, these are completely arbitrary names. That's what I was just saying. They're completely arbitrary names. As the Halliday and Resnick book says, with Gerald Walker, as that book says, they could have picked, instead of positive and negative, they could have picked something entirely different, like happy and sad. Okay? Or that's what you said yesterday, right? One of my students. And then I think our book gives two other adjectives, like chocolate and vanilla. You could literally have picked any names for these. All we need to know is that there's two kinds. That's all we need to know. We talked yesterday about what would the universe be like if there was only one kind of electrical charge, like all positives. Atoms wouldn't exist, right? None of nature would. So, two kinds. I believe the names positive and negative were dubbed by Franklin. But you'll have to do your reading to find out the exact historical names. And yes, we have reading quizzes. So there are many ways to classify materials, like wood and metal and air and water, right? There's many ways. You can say liquid, you can say gas, you can say solid, right? But there's another pair of adjectives you can use, and that's insulator versus conductor. Okay? So insulator just means it's non-conducting. And it means that it is a substance in which electrons are not free to move. So they're just not free to move. Okay, we'll talk later about what makes electrons want to move in the first place. Actually, electrons never sit still. We'll find out. What are some examples of electrical insulators? I'm sure you know some. I'll name one. Wood. Wood generally does not conduct electricity real well. Examples. Okay, so students contributed other ideas like ceramic, which is used in electronic components because they're not good at conducting. We heard distilled water. Pure H2O actually cannot conduct electricity under normal circumstances. We also had rubber, which is why they wrap our wires in rubber, right, to protect us from charges. Conductors are substances where electrons are free to move. I think I left an extra blank there. I'll just put free, cross that out. Okay, free to move. So like metal, different kinds of metal, right? We said water when it's not distilled, like if there's actually something in the water, salt content makes it conductive. Salt in water. So I'll put water, but then in parentheses I'll put impure. Okay, so other solutions for sure. I just use SOLN. For conductors, there's a special case, guys. There's two special cases. We have superconductors and we have semiconductors. I think you know probably what those mean. If conducting means the electrons are free to move, then a superconductor would probably bring that to a hyperbole state. Not only are the electrons, or they're not only just somewhat free to move. Now I remember what word I was going to put here. Somewhat free. Not only are the electrons somewhat free to move, but how would a superconductor behave? Superconductors lose the resistivity and conduct supposedly perfectly under certain circumstances. Semiconductors are purposely designed to only conduct when you want them to. Okay, so we don't need to give examples of this, but as you know, your computers are made with semiconducting technology, and your phone, and basically circuitry in general. So the goal is to create a material that when you want it to conduct, it will, and when you don't want it to conduct, it won't. Almost like a controlled conduction situation. And semiconductors have properties that allow us to manipulate when it will conduct and when it won't. All right, let's clear this out. Erase this real quick. Okay, so going on in your packet there, it says these properties arise from the constituents of atoms. So obviously what's going on here is the atoms themselves have the charged particles, right? So as you know, atoms contain protons and electrons, right? So, I mean, I don't really want to draw an atom for you. Even if I drew an atom for you, it would just be an example of a way to think about atomic structure. In actuality, atoms have a probabilistic shape. So in other words, nobody really knows what they exactly look like. And if you really want to look at p orbitals and all that stuff, you can go back to your chem book and look and see how the structure of the atomic shells looks, quote unquote looks. Okay? So that kind of thing is not necessary, but knowing that it's the electrons and the protons in atoms that give a rise to these conductions and insulation properties, that's what we're talking about. Think of it this way, the atoms in a material, right, will either allow their electrons to travel or they won't, right? And if the electrons are free to move, it's because the atom doesn't need them right now, right? So in a conducting metal, the atoms are free to move only because the electrons are free to move, only because the protons aren't requiring them at that moment. So they're free to go elsewhere. All right. Let's talk about conduction electrons. So any electron that's free to move and not, necessarily in orbit, is basically traveling from atom to atom, jumping from orbit to orbit, and just traveling along its way through the material. So we call that a conduction electron. And because it's moving, it's considered non-localized. So it is an electron, it desires to be near protons, but it's already being canceled out by the presence of other electrons. So it can just kind of make its way around. What is net charge? Well, net charge is something that happens when an object loses some electrons or gains some electrons due to some outside influence. For example, if you take a piece of glass, right, let's say just some kind of weird piece of glass, maybe a rod or something, and you rub it with silk, like a silk handkerchief, if you rub that on there, okay, back and forth, what's going to happen is the glass will give. Think glass gives. In other words, some of the electrons from the glass will end up on the cloth, and the cloth is removing those electrons from the glass. So what happens now is the glass has more positive charge than negative charge. So the electrons are leaving, and those are minus charge. The protons are staying, and those are plus charge. So when you strip off some of the electrons, well, guess what? Some of the protons are missing their electrons, and therefore the whole rod experiences a positive net charge. So you guys probably already knew that. You can also reverse this. Instead of using glass and silk, you can use plastic and fur. And fur gives. Forgives. Always forgive your offender, right? Try to be a forgiving person. Fur gives. Fur gives electrons now. So if you rub fur onto plastic, the fur gives electrons to the plastic, extra electrons that the plastic didn't really need, and those electrons then make the plastic rod negatively charged. So what's going on is you really just have a few extra electrons, if that makes sense. And it was given to the plastic by the fur. All right, and I'm sure if I was a little more experienced with these sorts of things, I would know which types of fur give the most electrons. I just don't know that. By the way, I mentioned this yesterday, rubbing the silk on the glass makes the glass positively charged, and rubbing the fur on the plastic makes the plastic negatively charged. How do we know that? Like, how do we know they aren't both positive? Well, if you take the glass rod and the plastic rod now and put them near each other, they'll attract each other. See? So we know they're opposite charges. How do we know that the electrons are leaving the glass to go to the silk? And how do we know the electrons are leaving the fur to go to the plastic? We can't see that happening, but through many, many experiments, scientists finally figured that out, that glass gives and fur gives. Okay? So that was, I'm sure, not how they first noticed these things. They probably just first noticed, hey, this plastic rod is attracting this glass rod. Or perhaps, wow, these two glass rods, we rub them with silk, they don't want to be near each other. They're pushing each other apart. So they noticed first that they were attracting rods or rejecting rods, but then later figured out who was giving who the electrons. That was, I'm sure, a whole different set of experiments. Okay, so the purpose of that last bullet was just to help you understand that some electrons can move around and some cannot. Anyone that can move around is considered a conduction electron, and those electrons can either be carried from one substance to another or taken from a substance, and thereby making objects feel like they themselves are charged. So like the glass rod feels like a positive, one big fat proton, with multiple charges on it. I probably shouldn't have said proton, because a proton has exactly a +1 charge. This glass rod probably right now has a lot of proton charge on it, if that makes sense. Same thing with this plastic rod. It has a lot of negative charge. We'll talk about charge quantization a little bit later. You could actually count how many electrons are free using charge counting. Okay, so that would be done through quantization. And it's approximate, but let's go now to isolation. Isolation just means you've taken an object that's got charge on it. Let's say it's that plastic rod. So remember the plastic rod, the fur gives, right? So it gives its electrons. If you take this thing and you hang it from a string in the middle of a room, right? It's not going to change its charge because there's nothing around it to steal its electrons. The only way it can lose those electrons, those extra electrons it has, is if something takes those extra electrons. So maybe if you walk up to it and touch it, some of the electrons will get on your body. Or maybe if you stick a wire up to it, some of the electrons will travel through the wire. But as far as we can tell, hanging it from the ceiling is just going to stay like that, right? And if it's in vacuum and there's no air to steal some of the electrons, those electrons should stay there forever, theoretically. Okay, so put that sucker in vacuum and hanging by a thread, Maybe some of the electrons will go into the red thread, but that thing's going to have a net charge for a very long time. It's going to stay like that. Okay, so that's called isolation. You separate it from anything that could steal its electrons. Grounding is completely the opposite of isolation. Grounding means you intentionally attach, a wire to it, and then you attach that to a large piece of metal or something. So we call any large thing that can receive electrons, we call that a ground. So it could be a huge hunk of metal, and it can take so many extra free electrons, it'll just steal all the extra electrons from the plastic. So those electrons will then travel into the ground. It could mean the physical ground of the earth, or it could mean a large metal object or large conducting body of water or whatever. But it will steal those extra electrons, putting the rod back to neutral. So when that happens, it's not like there's no more electrons, it's just there's no more net charge, meaning the electrons that are in the plastic rod are doing their thing, orbiting their nucleus, and they're not busy acting as excess charge. Okay? So there's still electrons in there, because there's still atoms, but there's no extra electrons, if that makes sense. So grounding is the process of removing net charge, you could say. But isolation and grounding are antonyms, almost. Conduction path is pretty obvious what that is. Conduction path. So if you attach the wire to the plastic rod, and the charges are traveling through that wire to the ground, that's the chosen conduction path. So the electrons, and this is pretty phenomenal, electrons just know the shortest path. They know which way they want to go to minimize their work. So they'll just travel in the fastest way possible into the ground or into the large metal object. So that whatever path they take is just called the conduction path. Now let's talk about induction for a minute. Induction, you can think of it as charges are set up by induction. Okay? So some things are charged because you rub them with fur or silk. You know what I mean? That's not induction. Induction is when you have, let's say, a plastic rod, right? Can't spell plastic today. There's a plastic rod, and it's not charged. It's just a plastic rod. It's not charged up at all. Maybe it was recently grounded, so it's totally neutral. And then along comes, like a metal sphere or something. Or let's not do metal sphere. Let's do metal sphere. And the metal sphere is intentionally positively charged. Okay? So somebody worked very hard to charge this little sphere. So they bring this sphere somewhere near the rod, and the closer you get, the more this happens. But you bring the plastic rod and the sphere close to each other, and what happens is the atoms in the plastic rod start to polarize. They're like, hold on, we don't want to be, the protons are like, we don't want to be near the plastic, or we don't want to be near the positive charged ball, because they repel. But the protons can't really move very well. They're so heavy. So the electrons do their thing, and they travel to this side, leaving their protons behind. So what happened there was a charge was induced. Now this object, this plastic rod, it's still technically neutral because it has equal number of pluses and minuses. But the pluses are on the right, and the minuses are on the left. So you could actually use that little plastic rod now as a charged object, as long as you keep, near one end of it. So, if you come over here, you would really feel like you were near a positively charged plastic rod. You know what I mean? On the other hand, if you went to the other side and you stood over here, you would feel like you're really near a negatively charged plastic rod. The truth is the plastic rod's truly neutral, but the charge was polarized. So it's like it has the illusion of being a charged rod because of the way it's separate. And this is called induced charge. It's a little bit different from rubbing it with fur or rubbing it with silk. So the word induction doesn't mean what it means in everyday life. In electrical theory, induction just means from a distance, you have created a change in a situation. So sometimes we induce a current. That means from a distance we set up a current. That was what was going on in that that Mobius strip car thing. He was setting up little currents inside that magnetic disk. But it was from a distance. It's through a field, actually, we'll talk about later. Okay, now, after you have charges stacked up, on objects, maybe one positively charged object and one negatively charged object, you start to notice that they behave around each other. So if you put, let's say you have two rods that are positively charged and one rod that is negatively charged. If you start putting these two near each other, you'll notice they start to interact. They'll actually pull towards each other. You put them both in outer space, where there's no other influences around, no planets, no stars, no gravity, roughly, they will literally eventually collide into each other. They want to come to each other. And the opposite is true if you put the two blues together. So if you put the two blues together, they will repel each other, trying to escape each other. Okay? So obviously this has been noticed long before it's been understood, right? People notice these things and like, dude, that's weird. My hair is standing on end. It's trying to get away from my body. Or they'll notice that this ball is like magically pushing this other ball across the table and neither of them are touching. Like, what's going on? So there's this imaginary interaction, or I shouldn't say invisible interaction, not imaginary. And we call it electrical force. And obviously the key is to understand that like charges attract and opposite charges, like charges repel, opposite charges attract. You guys know that. This is why they say opposites attract, right? Now this makes electrical force very different from gravity, because gravity, there's only one type of gravitational property an object can have, massness, right? If something has massness and something else has massness, they attract each other. End of story, okay? But in electrical theory, something can have chargedness and something else can have chargedness, and two things can happen. They can attract or repel. So because there's two kinds of charge, electrical charge, we have two types of interaction. And because there's only one type of mass, as far as we know, there's only one type of force, attractive force. So all the equations I'm about to show you match beautifully with gravity, except for one thing. Gravity always attracts. And strangely, electricity can be either attractive or repulsive. That's one major difference between electrical theory and gravitational theory. But the equations themselves, the names of the quantities, field, potential, energy, all the names are the same. The equations look almost identical. But there is that attractive and repulsive instead of just only attractive. So scientists are playing around with the idea that maybe there is a repulsive type of gravity, anti-gravity, antimatter, not antimatter, possibly other types of matter that repel each other. That would maybe answer some weird questions about our universe and its shape and size and stuff like that. But it's just theory, Let's go to the equations. So if you're trying to fill in equations, you remember that the force of gravity was G mass 1 times mass 2 over r squared. You probably remember that. Okay, well now, look at the equation. It's K, charge 1, charge 2 over r squared. It's the same equation. Instead of M1 and M2, we have charge 1 and charge 2. Q means charge. Q always means charge in this class. If you take a thermodynamic class, Q means heat. But in this class, Q means charge. The K is just a number. You probably remember that G was 6.67 times 10 to the minus 11th. Well, K is also just a number. It's 9 times 10 to the 9th. Okay? So it's just a different number. And then the charges are taking the place of mass. So we used to think in terms of mass 1 times mass 2. Now we're thinking charge 1 times charge 2. The r squared is the same as before. It's the separation distance between the two objects. Notice I put a magnitude symbol on here. See the absolute value bars? That means we're only talking about the strength of the force right now. So you'll notice there's no vectors here. Mrs. Roy did not put any harpoons on top of variables, no hats, no little vector symbols anywhere. This is just how big is the force. Is 1 Newton, 2 Newtons, or 10 Newtons? Well, usually they're actually quite small, so they're not anywhere near a Newton, but that's what that's answering. The next line there says F12 equals negative F21 equals, and then we put KQ1 Q2 over R squared R hat, where R is a unit vector given by pointing in the direction of the vector, or so I should just say a unit vector, not given. It should say a unit vector that points. It is a unit vector that points in the direction of the vector that points from charge 1 to charge 2. Okay, this is going to take a little bit of time to get used to, but basically it works like this. If you have a positive charge called Q1 and a positive charge called Q2, when I write F12, it's pronounced, and maybe you can even say this with me out loud. I'll say it first, and you can repeat it. F12 is pronounced the force on charge 1 caused by charge 2. I said that backwards. It's the force caused by charge 1 operating on charge 2. So just like sometimes you might push a friend and they might push you, when you push a friend, let's say your name is Tom and their name is Bob, force Tom Bob would be the force Tom puts on Bob. So the acting one is mentioned first. So F12 means force 1 on 2. So there's 2 charges. They're both experiencing forces. Now, the thing about Newton's third law, remember, I'm almost done. The thing about Newton's third law is that for every action, there's an equal and opposite reaction. So that's what this part means right here when it says F12 is the opposite of F21. It just means if there's a charge acting, let's say charge A is acting on charge B, well, charge B is also acting on charge A, and there's this equal magnitude of force there. Okay? So the only difference is the direction. In this drawing here, F12 is pointing to the right, trying to repel Q2 away from Q1. But if you're standing here on Q2, you would interpret it differently. You would say, hey, I'm on Q2 and we're pushing Q1 away. So if you're standing at Q1, you would say, charge 1 is pushing charge 2 to the right. But if you're standing at charge number 2, you would say, wait, charge 2 is pushing charge 1 to the left. So the first case is called F12 when you're standing at point 1. And the second one is called F21, that's when you're standing at point 2. And the only difference is the opposite direction thing. The force amount is the same. Which means that if you take this from a gravity standpoint, our Earth is pulling on the moon as much as the moon is pulling on the Earth right now. Both the moon and the Earth are pulling on each other with the same force. The only reason the moon appears to do all the moving is because it's so much lighter. And the same is true for charges. The more charged object will tend to look more stationary. And the less charged object will just like orbit around it or run away from it or whatever. So the one that moves more is the one that has the lesser mass and sometimes the lesser charge. Okay? So I hope I said that clearly. We'll pick it up from here tomorrow. I'm going to repeat what I said there on the like charges versus opposite charges. And tomorrow is mostly examples. So I have a few more comments to make. Like down below, there's a few more things to say, but that's pretty much the gist of the chapter. The rest is a lot of math examples. That's like the whole chapter, by the way, chapter 21. So in case you're worried about too much content, I don't think that's an issue here. I think there's only like 11 chapters, and I could teach a chapter every couple days, really. It's mastery that we need to worry about. Is it not stable?
Stable is bad.
Oh, sorry about that. I had trouble with the controller. All right, I'm going to cut off the last few seconds. Okay, so because of the charges that can accumulate by either gaining electrons or losing electrons, when you have more than one object and they each have their own net charge, let's say there's 2 objects, one's negatively and one's positively charged. A long time ago, people started to realize these are attracting each other. And the same is true if you have a positive on the left and negative on the right. So it didn't seem to matter where things were. There was some kind of attractive force. They even knew that the closer you bring them, the more intense the pull. You know what I mean? And then they also discovered that if both are positive or if both are negative, it's more of a pushing apart sort of thing. So that's why we say like charges attract, repel, and opposite charges attract. So that's just kind of where that comes from. When people say, oh, opposites attract, that's, I believe, kind of where that idea comes from. Okay, if you want to measure the force, that's where you need the math, right? So it turns out that just like in gravity, the force of gravity was gm1 m2 over r squared, where r is the distance between the centers of mass, right? And m1 is the mass of the first object, m2 is the mass of the other object. This will measure gravitational pull, and this, I think, was known as early as Newton. This is named after him, for sure, although I don't know how well he knew capital G at that time. But anyway, he knew that there was an inverse square relationship, and so he kind of knew this rule. And then the charge version of it is almost exact same thing. Instead of a G, we use a K, and instead of masses, we use charges. Okay, so that measures how strong the pull is. And I didn't write this down yesterday, but K is also known as 1 over 4 pi epsilon naught. We'll talk more about that later. But whether you call it K or 1 over 4 pi epsilon naught, either way, it's about 9.0 times 10 to the 9th. 9.0 times 10 to the 9th. And if you must know the units on K, you can figure those out because you have newtons on the left, right? And then you have this mystery K here. You don't know the units of K yet. But then here you have charge units. And for charges, by the way, we use coulombs. And then on the bottom, we're in the MKS system, so we use meters. So basically what you have here is newtons equals something times coulomb squared over meters squared. So if you kind of isolate the K, the unknown constant, you end up with Newton meters per coulomb squared. Newton meters squared per coulomb squared. So going back to K equals 1 over 4 pi epsilon naught equals 9 times 10 to the 9th, you could put in the units. It's actually Newton meters squared per coulomb squared. Like I said, who really cares? I mean, the units themselves of K aren't as important as simply knowing how to find the magnitude of the force. Sometimes we will use K, and sometimes we will use 1 over 4 pi epsilon naught. Okay? Now that's in the MKS system, where we're using meters, kilograms, seconds, and so forth. So sometimes we call it the MKSA system. You have not heard this yet because you haven't studied electrical yet. But the A here represents amperes. Amperes, named after, you guessed it, Mr. Ampere. And the ampere is considered a coulomb per second. A coulomb per second. So if you're using MKS units, it's sort of traditional to use coulombs for charge because really it's not the MKS system, it's MKSA system, and we use amperes. So amperes uses coulombs, and therefore coulombs is the right thing to be using. You do not have to measure charge in coulombs. You can measure charge in how many electrons you have. So if you have 5 electrons, you can call it 5 what? 5 elementary charges, we call them. So later we'll use elementary charges also, but for now, we're just going to call them coulombs, coulombs, coulombs for charge. Newtons for force, meters for distance. Okay? All right, so I didn't mention that yesterday, so that's kind of new. And then, because of Newton's third law, F12 and F21 are going to be equal and opposite. So I wrote that here in typed font. But all I'm saying is that when one object's repelling another object, the second object is also repelling the first object. In fact, they're both repelling each other with the same force. Okay? Whether they'll both accelerate or not depends on their masses and other things, but they are always pushing with equal and opposite forces on one another. You guys know that every time you push on a rock, the rock's pushing back at you, right? So if the rock's a small rock, the rock will move and you won't. If the rock's a big rock, you'll move and the rock won't. Right? That's a mass consideration. But the forces themselves are equal and opposite. So if you want to include the direction of the force, you include an r hat. So r hat is a unit vector pointing in the direction of r, or pointing in the direction of the vector that points from charge 1 to charge 2. So usually we just go like this, k q1 q2 over r squared, and then we put this little r hat here. And r hat just tells us which way it's pointing. So it might be radially away from charge number 1, or it might be radially towards charge number 1. But the r hat reminds us that it is a radial thing. You're either approaching a particle or you aren't. You're either approaching it or you're going away from it. Those are the two directions. So it's not left and right, it's sort of in and out. In and out, towards the charge, away from the charge. Okay, so we'll talk more about unit vectors later. R hat has magnitude 1, because it's a unit vector. So we could write that like this. The magnitude of r hat is 1. And then some teachers use, for magnitude, the double strike bars. I don't know which one your physics teacher used last year, but I'll just use the double strikes. And then also, if you put it in polar coordinates, think of it this way. You can write r hat as cos theta sine theta. So r hat is its own little vector, cos theta sine theta. And if you find the magnitude, you square root the sum of the squares. And indeed, it's 1, because square root of 1 is 1. So anyway, if we do need polar coordinates, we will use r hat as, instead of, I hat, j hat. So instead of using, I plus j to represent r hat, we'll use cos theta comma sine theta. And if we're in 3D, we might have to go all the way to like spherical coordinates and stuff. So that may happen, but not today. Not today. Okay, let's go to comparing. So we were going to compare which is stronger, gravity or electrical force, right? And just from your common everyday experience, you think gravity is a strong thing. You're like, oh man, I don't want to fall off that cliff, right? But if you fall off a cliff, right, what is it that really kills you? If you fall off a cliff, is it the gravitational force? Let's think about that. So gravity will accelerate you toward the ground. You don't need electrostatics for that. Gravity will do that all on its own. You have mass and so does the Earth. So guess what? You're attracted. And you move fast. After a few seconds, you reach terminal velocity. You don't go any faster maybe. But you will eventually hit the Earth. Now, if gravity is so very strong, it should pull you all the way to the center of the Earth, wouldn't it? So what stops you? What makes you hit the ground and stop moving? Why do you stop moving? What would cause your speed of 120 miles per hour? What would cause that to drop instantly to 0 miles per hour in less than 1 second? That must be some impulse force. That must be some powerful impulse force. Remember, impulse will change momentum, right? And if it's a force executed over a short amount of time, that's a high impulse. So some of you need to go back now and read up on impulse force. Impulse force in your mechanics book, okay? Quick show of hands. So this must be some serious impulse force. So what is causing it? What brings your velocity from 120 miles per hour to 0 in less than a second? Less than half a second. It's electric repulsion. It's electric repulsion. When your body hits the ground, the atoms in your body and the atoms in the ground come together. And what keeps you from going through the ground to the center of the Earth is electrical repulsion. The nuclei of the atoms in your body, your skin primarily, and the nuclei of the atoms in the ground are literally repelling each other. And which force eventually won? Did gravity get you to the center of the Earth? No. Which force actually won? Electrostatic. By a mile. Stopped you instantly. So right there you get a sort of a real subtle glimpse of how powerful the electric force is. So now we're going to actually measure it. So we're going to need to know some things. We're supposed to compare KQ1, Q2 over R squared versus gm1 m2 over r squared. We'd like to compare these. Now, there's two ways you can compare numbers. You can subtract them and find their difference, or you can divide them and find their ratio. You'll notice in our homework that often they want you to divide them to find the ratio. So instead of saying things like, hey, this is 4 newtons stronger, you say something like, oh, this is 4 times stronger. Different language, right? Okay, so we're going to end up dividing these. We're doing electrical and gravitational. So let's just consider it force of electrical to gravitational. So we'll put the division here. We're going to divide these. So the first thing we notice is that the r squareds cancel out. The distance between the centers of the electrons, it doesn't matter if you're measuring gravitational force or electrical force, the two electrons, we'll call E minus and E minus, whether you're thinking about how massive they are and how far apart they are, or whether you're thinking of how charged they are and how far apart they are, either way it's the same distance apart. So that r is the same r. Okay, so this is what we're going to try and find right now. It's going to be the ratio of K, Q1, Q2 over G, M1, M2. That's what we seek to find. And these are electrons, well-known objects in our universe. K we said is 9 times 10 to the 9th. G is 6.67 times 10 to the minus 11th. You probably barely remember that number because it was last year. And I think they just give it to you on the AP test, right? So you don't have to memorize that much if you're an AP physics student. I just remember having to memorize it myself because I actually never took an AP test when I was growing up. So I had it well memorized. And now, what about the charges on an electron? Well, they're both electrons, so they're both negatively charged. And then you're going to have to look this up. What's the charge on an electron? So this is where Siri and Google will just answer you verbally. You know what I mean? So I'm going to ask Google, what is the charge on an electron? I already know, but I'm just going to... So it's 1.60 times 10 to the minus 19th, and that is a Coulomb charge. These are both electrons, so we have another one of these factors. Notice a Coulomb is actually a rather large charge. Basically, you need 10 to the 19th electrons to even get 1 Coulomb. Okay, and then M1 and M2, oh boy, these are going to be real small masses. Let's see how much mass an electron has. So let's go back to Google. This one, I want to say 10 to the minus 24th kilograms, but I honestly don't remember too well. Let's see. What is the mass of an electron? She'll answer out loud if I have my volume turned up, but I told it silent. So it's 9 point, I was wrong. It's 10 to the minus 31st. I thought it was 23rd. Okay, really small kilograms there. That's kilograms. It's actually 9.11 if you're doing 3 sig figs here. Okay, this does need to be typed, okay? And you do get a positive ratio because the two negatives cancel out. Yes? Okay, so if you type all this, okay, so you do not need a calculator for the 10 to the whatevers. So you have 10 to the minus 9th, you have a 10 to the minus 19th, another 10 to the minus 19th, you have a 10 to the minus 11th, you have a 10 to the minus 31st, and a 10 to the minus 31st. So if you look at the top, you basically have 10 to the minus 47. Because you're just combining negative 9, negative 19, and negative 19. That's negative, hold on, negative, oh, this should be a positive 9. Mr. Shore messed up, that's a positive 9. So think of it as positive 9 and you're subtracting 38. So this is 10 to the minus 29, right? Then the bottom is 10 to the minus 11th, 10 to the minus 31st, 10 to the minus 31st. So that's 10 to the minus 73. Okay, so you got the orders of magnitude. 10 to the negative 29 minus negative 73. You can already tell this is on the order of 10 to the, and then 73 minus 29 is 44. So is it 10 to the 44th? Well, it's something near that. So now let's do the other numbers. We had a 9 times a 1.6 times a 1.6 on top, and then we have a 6.7 times a 9.1 times a 9.1 on the bottom. We get 0.04 times 10 to the minus 10 to the 44th. So in scientific notation, you would move the decimal 2 spaces to the right. So now that's just a 4. But to compensate, you would subtract 2 from the powers of 10, so it'd be a 42. So you can see this is a very, very, very large ratio, like really big. And I can't stress enough how much stronger electrostatic force is than gravity. There was another clue all along, by the way. There was another clue all along. Before all this calculation, just look at K versus G. You know what I mean? K is 10 to the 9th. I'm talking positive 10 to the 9th. 9 times 10 to the 9th is 9 billion. Newton Coulomb squared per meter squared. G was already 16 orders of magnitude less than that, at least. See what I'm saying? Or about, I mean. So that was a clue already, but until we included the masses and the charges, we couldn't really see the whole truth. The correct ratio is this, 4 times 10 to the 42nd power. So I see some... All right, so let's go now to our next thing. Our next comment is, so the electrical force between two electrons is about 10 to the 42 times stronger than the gravitational force between them. All right, now the scope of Coulomb's law. When are you allowed to use this KQQ over R squared rule? Okay, there is a rule on that. You may not use that rule unless you're dealing with point charges. That means literally charges with no noticeable size or uniformly charged spheres. This is really important, okay? This is also true for gravity, by the way. When you measure a force of gravity or a force of electrostatics, you're supposed to use round objects that are uniformly distributed. For example, let's talk gravity. It's a little bit easier to understand. Let's say you have a ball, and it looks like a regular bowling ball. But when you roll it down the lane, it like wobbles badly. Okay, that means something. That means somewhere in the ball, there might be a pocket of air. Like a bubble was formed when they poured the metal, or I guess it's a plastic, right? When they pour that plastic bowling ball, they accidentally got a bubble in there, so it's not rolling straight. Okay, you cannot use GMM over R squared as easily in that situation. You can use that idea, but it's probably a little bit risky to just treat it like a single point charge. I don't think all the charges, or point masses, you can't think of all the masses at the center. Okay, so if there's like a little pocket of air in there, you cannot think of all the mass as centrally located. And that kind of messes up the rule itself. The same is true with charges. If you have like a metal ball and you put some electrons on it, we'll talk about this later, but the electrons will all spread themselves out beautifully uniformly across the surface. And then you can use Coulomb's law because it's all uniformly distributed. Okay? And even if it's like an insulator, and it's got negative charges all throughout it, even on the inside of the volume, as long as it's uniformly distributed, you can treat it with Coulomb's law. Okay, so it works for tiny points, and it works for round objects with very beautifully distributed electrons. And the same is true for gravity. Once you start getting weird shapes like this, and some of the charges, like some of the net charges on this side, and then some of the net charges on this side, and some's positive and negative, and maybe there's more electrons on one side than the other, that's when Coulomb's law isn't meant to be used straight up. You have to use vector math to work with that kind of situation, and integration, actually. Okay? So use it for small charges, one with another. Use it for perfectly round spheres that are uniformly charged. And there are two shell theories. This is very important. Okay, these are also mentioned in the gravity section. If you go back to the gravity section, you'll see them. All right? Anytime you have a shell like this. So the first shell theory just says if you have a uniformly charged object and you're outside over here at point P, you can just think of all of these charges as centrally located. You don't have to think of it as a ball. You can think of it as a dot, point Q or whatever. And then if you are inside the shell, this is the second shell theorem, if you're inside the shell anywhere, and it's a hollow shell, you will experience no forces at all. You will experience no forces at all. All right. Transfer of charge to equilibriate. This is important. If you take a metal object, whether it's hollow or not, and you dump a bunch of electrons on it, maybe it's because you rubbed it with something. Or maybe you did an experiment where you charged it up with wires and then you quickly remove the wires. Now it's all charged up, right? So what happens to these electrons? Well, they're on the shell and they're perfectly stuck there. They can't get away. But they're going to do two things. One, they're going to try to repel each other, and therefore they're going to spread out. So they're going to definitely spread out from one another to get as far away from each other as possible. And also, none of them will dare enter inside the conductor. So they're not going to go inside the conductor. Because if they go inside the conductor, then they're close to other charges. So if you could kind of see this from the backside, if you could go around the backside and look, you'd see the same picture. All these charges hiding on the backside of the ball. Why? Because there's charges on the front side of the ball, and they're trying to get away from the ball, from those. So every electron is trying to escape every other electron, so they spread out as far as possible. No one dares go inside the conductor, because if they do, then they're closer than they need to be to the other side of the ball. Okay? As soon as you enter a sphere, you're already closer to the other side than you should be, right? So all of the electrons go straight to the surface instantly, and then they spread out completely. So this is another reason why there's no forces on the inside of the ball, because they all spread out and they escape each other and go to the surface. And once they get to the surface, they spread out again and space themselves equally across the surface area. Okay, so that's called transfer of charge to equilibriate, and net charge is distributed over all the surface of the object. Okay? And this is in the case of a conductor where the electrons can move. Sometimes you can make like a jello kind of thing with charges in it, and then you freeze it as a solid or whatever, and now the charges can't move. They're all kind of stuck close to each other. Oh, well, too bad. But if they can move, they will, and they'll go away from each other, distributing across the surface first, and then on the surface, escaping each other as best they can. Okay? Any questions on that? All right. Almost done with this whole chapter, actually, and then we'll do examples. Non-conductors do not distribute their charges. They can't because the electrons aren't free to move. So you can actually have pockets of net charge. So if it's an insulator, then you can have the object, and have like a lot of positive here, and then just a little bit of positive here, and then like a ton of positive here. But this has to be on an object where the electrons can't move. As soon as the electrons are mobile, man, they are going to distribute things evenly and balance things out for you. Okay. If you see the word current, this is a little early to be talking about current. It's basically the amount of charge that passes through a single point in a certain amount of time. Okay, so current is what it's just what it sounds like. You're standing on the beach and water's flowing by you, right? The ocean's moving the water. Well, when electricity flows past you, you could count how many electrons go by in a minute or whatever, or how many coulombs pass by in a second. If you measure how many coulombs pass by in a second, that's using the ampere measure system. So if it's 1 coulomb that passes by in 1 second, we call that 1 ampere. Or we just call it an amp. An amp. Okay? So current's kind of a brand new quantity because in the past we've studied things like meters per second and stuff like that. We've never done like mass per second, and now we're doing charge per second. So it's like a brand new thing, and we would